I feel a bit like a fish out of water here in that I'm on the other end of the fire hose from the other speakers. First of all, I'm not a CEO, I'm a retired physics professor. And secondly, I'm not here to promote an intervention, I'm here to receive one, so to speak. And that in about 3 or 4 weeks, sometime in November, I'm going to be doing the first stage of a mitochondrial replacement therapy that hopefully will do something to deal with my advanced age. I should say that I am presently 90 years old. My birthday is in a week and I'll be 91. And Dennis was talking about the FDA moving slowly and maybe they might do something in 20 years or 10 years or something like that. I don't think I have another 10 years, so I want to do something immediately. Okay, now, the rest of the biotech world is talking about interventions that might eventually fix the problem. But I'm a volunteer risking my 90-year-old body and my health and my remaining years to actually do something. Let me talk a little bit about my background. I'm a PhD in experimental nuclear physics, and I got my PhD in 1961, and I've been teaching from then to when I retired from teaching in 2010 when I was 75 years old. My research program continued for about another 8 or 10 years. But more recently, and I've done various experiments at some of them at big laboratories like CERN and Brookhaven, and I've also delved into the interpretation of quantum mechanics, and I actually did an experiment testing whether one could use quantum entanglement to send messages faster than light and backwards in time. The answer is no. And I've written 3 science fiction novels. I write a column in Analog magazine, published every other month, usually about science, and many of them are about the kind of stuff we're talking about here, namely interventions that might do something to help with aging. Having retired, I was able to write a book I'd been planning for a long time about my interpretation of quantum mechanics, which is a way of looking at what's going on in the weird world of quantum mechanics and understanding things like non-locality and entanglement. As a result of the stuff I'm going to talk about earlier, I think I have a certain perspective about how aging actually works and how to fix it. And so I wrote a book about it, which is going to be published by Springer sometime early next year, and I'll tell you a little bit more about that later. As I said, I was born on October 24th, 1934, and with my advancing age and my retirement from active physical research, I began to ask some questions about what was going on with my own body. First of all, what is human aging? What's the underlying driving mechanism? What can be done to slow it down or reverse it? And what's the upper limit? Why is there an upper limit to human age of around 120? And what sets that limit? And so I started reading the biotech literature. And as most of you probably know, it's not easy to do that because they use their own lingo, and it's sort of like reading a foreign language to a person like me. And so I had to spend a lot of time trying to understand exactly what these funny words meant that I'd never heard before and what was going on. In trying to figure out what was the basis of aging, I went through telomere length decrease, senescent cell accumulation, progressive epigenetic reprogramming from a young profile to an old profile. And these all seemed interesting relations having to do with aging, but they all looked like downstream effects of something. And then I came to mitochondria. And the interesting thing is that mitochondria damage easily and they supply all the energy to the body. So when they get damaged, the energy goes away and you have a problem. And the body deals with it perhaps by shutting down the mechanisms, the repair mechanisms we have when we're young and so forth that allow one to fix the problems as they arise. So when the repair mechanisms shut down, you get older. And that's the sort of working hypothesis. As a physicist, we often tell one another we should follow the energy. And my feeling is that that's what one should do in the case of longevity as well. Energy is very important and it's often ignored. And mitochondria are the principal, almost the unique source of energy in cells, and when the mitochondria get damaged, everything else degenerates. Okay, so having taken this point of view, I started looking into what could be done about it, and I discovered Mitrix Bio, which has a procedure for replacing mitochondria. And they actually mapped my mitochondria as shown in this slide. This is a scan of the 16,569 base pairs that make up my mitochondria. The ones above the line are undamaged. The ones below the line have something wrong with them. Ignore the white stuff here, which is just an artifact of the measurement. Yeah, thank you. The significance here, and you can't see it very well because the slide's a little out of focus, but there are little colored dots around in here representing point mutations in my mitochondria. The important things, though, are the black lines. These are deletion mutations. These are things where a certain string of base pairs in the mitochondria are missing. And I'll tell you why that's important later on. But they're the most damaging kind of mutations in the long run, and probably the things that contribute to the setting the 120-year limit to how long we can live. The point is that when a mitochondrial DNA is mutated, a piece of it is missing, and so the little ring of mitochondrial DNA gets smaller. These DNA are being replicated continuously all the time, and when they get smaller, they replicate faster. When they replicate faster, they can win the race against the other guys and can take over the whole population. And this generates an exponential increase in the mitochondrial DNA that has deletion mutations. This is a slide from a German group that measured the deletion mutations that are greater than 3,000 base pairs. In other words, something like 12% or more of the mitochondrial DNA is missing from these rings. And this is starting around age 20 and ending around age 80. And the red line is the fit that I did using Mathematica to their data up to age 65. I included this point and so forth. And one way you can talk about exponential decay is by talking about what the doubling time is, exponential increase. For example, inflation is an exponential increase. Human population is an exponential increase. Moore's law in electronics is an exponential increase. They all have doubling times, the time it takes for whatever you're measuring to go up by a factor of 2. Before age 65, the deletion mutations rise double every 11.81 years. In other words, about every 12 years, you have twice as many of these mutations as you did before. On the other hand, above age 65, it sort of takes off and goes up through the roof, and the doubling time goes down to about 3 years. That means that every 3 years, you have twice as many of these mutations as you did the time before. You may have noticed in your elder relatives that up to about age 65, everything goes nicely along. Maybe you're losing a little bit, but it's not really a very big deal. And then suddenly something happens and you sort of hit the wall and things get worse in a big hurry. This is this exponential increase that we're seeing here. So from the point of view of energy, the question is, when the energy goes away, what is the consequence of having your energy depleted? Well, if you want to do an intervention, the problem is that interventions cost energy. I'm using a thing that I invented called a mitochondrial unit, which is 10 to the 9th, the energy supplied by 10 to the 9th ATP molecules. And for scale, sort of a young body cell uses about one of these a day. An old somatic cell, the energy use goes down by a factor of 2 or more, and it needs this much just to stay alive. Okay, so what about the interventions? Well, telomeres are okay. The telomere lengthening is okay. It doesn't cost much. Senescent cell apoptosis, the idea that you stimulate senescent cells to go away by causing the body to remove them in a nice, clean way, requires almost one of these units to function. And epigenetic reprogramming takes a lot more. So the moral is that if you try these interventions for a very old person where there's not much energy left and the energy is being used to stay alive, for the cell to stay alive, you're likely to run into problems. It isn't clear exactly how much energy is required. I mean, what happens when an epigenetic reprogramming is in progress and suddenly there's not enough energy to support it and it has to stop in the middle. But whatever that happens in that situation, it's not going to be very good. Okay, so the point is that point mutations increase linearly while deletion mutations increase exponentially. So what can be done about it? What can you do to fix the problem? One possibility is using young plasma. There are companies that will recruit college students and so forth to donate their plasma and replace it and extract the plasma and then give it to an older person in order to help them along. And this represents a certain amount of mitochondrial transplantation. But if you give 2 liters of young plasma, you get about 2 milligrams, which isn't very much, of mitochondria, which isn't very much. Stem cell transplantation is a little better. If you transplant 10 to the 9th stem cells, you get about a quarter of a gram of mitochondria. Platelet infusion with 2 apheresis units gives you about a gram. But what you really need is a lot more than that. And we're looking at, Mitrix is looking at transplanting mitochondria at a much higher level, about 200 grams in a dose, and that might do the job. The point is that 10% of your body weight is in mitochondria. So if you want to add 25% mitochondria to an 80 kilogram human, you need to transplant 2 kilograms of mitochondria. You're not going to get that from a donor. And so the only way of doing it is by using a bioreactor. Whoops, I guess I don't want to go there yet. By using a bioreactor which multiplies the mitochondria to the point where you can do that level of transplantation. And sometime in November, I'm going to have the first preliminary tests with a much smaller amount of mitochondria, and we'll see how that goes. First of all, one has to establish the safety before going on to do the real work of doing age reversal. Now let me tell you a little bit about my book. It's 60,000 words. The title is How to Live Much Longer, the Mitochondrial DNA Connection. It's to be published early in 2026. And these are some of the topics covered, which in the interest of time I won't tell you about unless you ask. But one of the interesting things that came up is the idea of sports doping. James McCulley, one of the pioneers of mitochondrial transplantation, got written up for his work in treating the hearts of babies that had heart problems and getting them going again. And immediately he was contacted by athletes who wanted to use the same techniques to improve their performance. So one can anticipate that if and when mitochondrial transplantation becomes easy and it's around a lot, you can bet that all of the sports figures who would like to extend their sports span by a bit are going to be knocking on the door and using these things to boost their performance. Anyway, for those who are at this meeting who would like to have a free PDF copy of my book, this is my email address. Send me email and I'll send you a PDF copy for free in advance if you're interested, but as long as, with the understanding that you don't pass it around, but keep it for yourself. Okay, so this is the next to last slide. These are questions that maybe we can answer by doing mitochondrial transplantation and seeing the results. First of all, does it truly reverse human aging? How important is it to match the haplogroup of the mitochondria that goes in with the haplogroup of the recipient? I can talk about possible problems in that area if somebody's interested in asking. After you restore the energy by fixing the missing energy problem of mitochondria making ATP, do the repair mechanisms that have been shut down due to aging, do they come back online, or do you have to do something else? This applies to buildup of senescent cells, it applies to epigenetic reprogramming, and so forth. Okay, the final slide is concluding. Our working hypothesis is that accumulated mutation damage in mitochondrial DNA is the root cause of human aging, with all of the other so-called hallmarks are downstream effects of cellular energy. The cellular energy can be restored by transplantation of good mitochondria produced in a bioreactor. In a few weeks, I will start the first phases of this kind of process. And finally, there are five openings in this initial program for sponsors who can participate if they're willing to support the process. I'll stop there and answer questions.
One question. Hi, thanks so much for a great presentation. I'm Dr. Kristen Glorioso. I'm the CEO of NeuroAge. And I just have a question. What is your secret to seeming so young? I would have thought you were 65.
Say again? Why is 65 a kid?
You look 65.
There's not any good explanation for that, but I have a hypothesis. That is, there's a process called mitophagy, where the body automatically senses bad mitochondria that don't have the right intermembrane potential and summons the troops to gobble them up, and they get replaced. Mitophagy requires a certain amount of available energy, and when the energy drops below a critical threshold, the mitophagy gets shut down, and then the exponential takes off. And I think that's what's going on, but that's a research topic rather than a proof. So, but yeah, I think that's why 65 is important. I take metformin, which improves your mitophagy, and maybe the reason I've managed to stay around so long is because the metformin is keeping my mitophagy operating longer than it does for most people. I don't know.
Thank you.